This video is not simply a history of multi-celled life. Rather, it is an attempt to produce analytical tools that will aid in its understanding. My thesis is that the history of multi-celled life on Earth is one of successive, biotic ages, being cut short by major extinction events. I will justify it in two parts. I will first give theoretical grounding to how that process occurs. Afterwards, I will show how the theory explains the development of life in the past 575 million years. The biosphere is the space on Earth's surface containing all living things. It interacts with three other spheres: the atmosphere, hydrosphere, and lithosphere. The lithosphere refers to the Earth's crust, made of rock and soil. Oceans, lakes, and rivers make up the hydrosphere. All of them are enveloped by a mass of gases called the atmosphere. Together, these three spheres come together to support the biosphere. Atmosphere can influence the biosphere by blocking light or trapping heat. Events in the lithosphere like volcanic eruptions can also influence the biosphere. By definition, the biosphere is what contains all living things. Living things are characterized by 7 processes. They can move, respire, sense their environment, grow, reproduce, absorb nutrients, and remove metabolic waste. How living things go about performing those processes is determined by their traits. These can usually be passed on from parent to offspring during reproduction. Living things belong to the same species if they have the same traits, can mate to produce fertile offspring. Individual members of a species exhibit slight differences in their traits. Those with traits best enabling them to carry out the 7 life processes in their environment stand a better chance of surviving to reproduce. They are more likely to pass those traits on to their offspring. Thus, these beneficial traits become more common in each successive generation. The continual change that results is called evolution. It produces new species in a process called speciation. Species can also be lost. This occurs in a process called extinction. Something important to understand is that speciation and extinction are twin engines. They control how diverse life on Earth is. This occurs in a continuous, ongoing process. Speciation increases biodiversity, whereas extinction decreases it. The balance between speciation and extinction measures how biodiversity changes over time. If the rate of speciation is greater than the rate of extinction, net speciation occurs. That means that biodiversity increases over time. If the rate of extinction is greater than the rate of speciation, an extinction event occurs. The above facts are helpful when looking to understand how the biosphere has changed historically. The functioning of biosphere is dependent on flow of energy throughout it. Energy comes from a source. For simplicity, we'll only consider the sun, but know there's also chemical energy. Producers like plants store it in glucose during a process called photosynthesis. It then passes on to primary, secondary, then tertiary consumers. This flow can be represented on an energy pyramid depicting each of the trophic levels. Much of the energy is lost to the environment during respiration. At each step, only 10% of the energy is passed to the next successive level because higher-level consumers are more dependent on the stability of the whole system. They are generally more vulnerable to extinction. In the fossil record, there are periods when biodiversity noticeably declines. For example, around 65 and 200 million years ago. It eventually bounced back each time. The goal is to develop a model that explains this process of rise and fall. In my view, the story of life on Earth is of successive, biotic ages being cut short by major extinction events. It is important to clarify what this argument means and what this process looks like. A biotic age is a long period where multi-celled organisms experience an increase in biodiversity driven by net speciation. The competitive exclusion principle states that 2 species cannot occupy the same niche. It follows then that in a finite space like the biosphere, the number of available niches would gradually shrink. The consequence of this for evolution is that the rate of net speciation gradually drops. This creates an initial phase of rapid net speciation and a later phase of slower net speciation. At the start of a biotic age, there is relatively little biodiversity, at least compared to later phases. There are very few species on the higher trophic levels. Because there are a lot of vacant niches, global biodiversity rises sharply. It is here that the higher trophic levels emerge or resurge. The Biotic Age's definitive life forms evolved during this very early phase. Afterwards, there usually comes a phase characterized by a slower net speciation rate. Here, biodiversity grows increasingly slower. Taken together, these initial phases have taken up about 95% of the biosphere's history since the Avalon Explosion. A biosphere's evolution is initially driven by the gradual biospheric process of available niches shrinking. Eventually, though, a cataclysmic event from outside the biosphere occurs. Something interesting to note is that the competitive exclusion principle can never stop speciation. It can slow down speciation but not stop it. This is because the principle also drives the process of niche partitioning. This is where interspecific competition is resolved by the species using the same resource differently, thus allowing them to coexist. As niches close up, net speciation can get closer to, but never equals zero. In practical terms, this means that the phase of slower net speciation can theoretically last forever. It only ends if a catastrophe occurs from outside the biosphere. Once it does, however, net speciation abruptly ends. Niches left vacant just before the start of the cataclysm close up permanently. This marks the end of the Biotic Age and the start of a major extinction event. The niches left vacant just before the cataclysmic event are not the only ones assaulted by it. Even some of the occupied niches become untenable. The rate of extinction comes to exceed the rate of speciation. The biosphere experiences a decline in its biodiversity, with higher trophic levels being hit the hardest. This decline is more so the product of the cataclysm's abruptness, not the specific changes it brings about. At some point, the major extinction event ends as abruptly as it begins. By that point, a lot of niches are left vacant. There is very little left in the way of higher-level consumers. This is a similar condition to that present at the start of a biotic age. As a result, there is often a 1 to -1 overlap between the end of a major extinction event and the start of a successive biotic age. If you're enjoying this video so far, like and subscribe. We know from the fossil record that the Earth has indeed passed through several biotic ages. The start and end of a biotic age is usually defined by a major extinction event. Smith 609 made a photograph documenting the extinction rates of marine genera from 542 million years ago onwards. The values will be used as a proxy for extinction rates in the biosphere as a whole. It shows numerous spikes in extinction rates. Of them, what does and doesn't count as a major extinction event is defined by the following, somewhat arbitrary criteria. 1. The spike in extinction intensity must exceed 25%. 2. Any such spikes with a gap of 10 million years, or less between each other, are considered part of the same major extinction event. Our focus for today will be on major extinction events only. Still, it's important to note the following for extinction spikes that don't exceed 25%. If the spike falls between 15 and 25%, it constitutes a minor extinction event. Those will only be discussed in videos focusing on specific biotic ages. Spikes falling under 15%, though, won't be considered as they leave too little an impact to be worth discussing. From the photograph, we could conclude that the biosphere has gone through 7 biotic ages, separated by 6 major extinction events. The photograph is unfortunately not comprehensive. It omits an earlier period that has the characteristics of a biotic age and even ends with a major extinction event. This is because it only starts at 542 million years ago. It is clear then that there have been 8 biotic ages and 7 major extinction events. For billions of years, there was no life form on Earth larger than a single cell. Multi-celled life seems to have first appeared around 1 billion years ago. The first fossils of red algae date to around that time. From 1 billion years ago to 600 million years ago, multi-celled life remained simple and limited. This changed when the oxygen level went from 3 to 5% around 575 million years ago, fueling the Avalon Explosion. It represents the first diversification of multi-celled life. Rapid changes in ocean life occurred. In the deep oceans, the first bilaterians appeared, likely living as burrowing animals. Of particular note, however, was the emergence of the first frond-shaped organisms, such as rangiomorphs. They are the definitive life forms of the first biotic age. In rougher waters, frond-shaped organisms were represented by petalonymids. In these shallow depths, they coexisted with even more exotic forms, such as Dickinsonea and trilobizoans. The first biotic age came to a close around 540 million years ago. This was when a cataclysmic event from the lithosphere devastated the biosphere. A deep rift widened in what is today Oklahoma. Lots of lava rose up, about 2,000 cubic kilometers of it. The simultaneous release of carbon dioxide and sulfur dioxide caused first a volcanic winter, then a period of sharp global warming. Oxygen levels dropped in the oceans. These events brought net speciation to an abrupt halt, marking the start of end Ediacaran extinction. With less oxygen, many occupied niches became untenable. Almost all of the species of the first biotic age, 80% to be specific, disappeared. Bilaterians managed to survive, however, and moved closer to the shores. The second biotic age kicked off with a biodiversification event that is generally more well known than the Avalon Explosion. It seems to have been driven by two major developments. The first was the development of calcified shells. This innovation likely occurred at the tail end of the first biotic age, as exemplified by fossils like the Mapoichia and Cloudinia. These shells offered protection from predators, forcing them to find new ways around those defenses. This may have directly led to the second major development, the evolution of eyes. Eyes gave secondary and tertiary consumers increased hunting accuracy. This forced their prey to become faster, as well as to develop armor and camouflage. The resulting evolutionary arms race continues to this day. It is responsible for much of the biodiversity that is observable in the world. The Cambrian explosion saw the rapid diversification of the bilaterians that survived end Ediacaran extinction. Most of the new, complex forms that evolved, like trilobites for instance, had calcium carbonate shells. Almost all animal phyla existing today can trace their earliest representative to this event. This fact probably explains why the Cambrian explosion is more well known than the Avalon explosion. Since almost all animal groups originate from the Cambrian explosion, it is easier to teach it as the beginning. Archaeocyathids, the definitive life forms of the second biotic age, first emerged in Siberia around 525 million years ago. They rapidly spread and diversified around the globe, creating the first ever reefs. For reasons that are still very mysterious, Archaeocyathids went into a sharp decline around 515 million years ago. This event was the start of the mid-Cambrian extinctions. The mid-Cambrian extinctions started with the disappearance of Archaeocyathids. Though devastating, it was quickly revealed to only be a premature dress rehearsal for a much larger spike in extinction intensity. Around 510 million years ago, massive volcanic eruptions occurred. They were caused by the placement of the Kalkanji large igneous province. Large amounts of greenhouse gases were released into the atmosphere. This caused increased temperatures in the oceans while simultaneously lowering the oxygen they had available. Many niches became untenable. Some 40 to 45% of marine genera went extinct in what is commonly known as the end Botomian mass extinction. By the end of the mid-Cambrian extinctions, all species of Archaeocyathids had gone extinct. Life quickly recovered following the mid-Cambrian extinctions. With Archaeocyathids gone, common sponges rapidly diversified in their place. Many of the new forms that appeared can be found in the Burgess Shale in Canada. Dated to around 505 Maya, it shows some of the third biotic age's most iconic creatures. These include Opabinia, Marella, and Pichia. Pichia is particularly noteworthy as it is considered a distant relative of vertebrates. The third biotic age is the shortest lived of all biotic ages. Lasting only 10 million years, it ended at the onset of low oxygen conditions in the hydrosphere. The last Cambrian extinctions refer to two major spikes in extinction intensity separated by about 10 million years. A sudden drop in oxygen levels led to the first spike, known as the Drebaschian extinction event. It killed off some 40% of marine genera. The anoxic conditions persisted in the oceans, but extinction wasn't punctuated again until about 490 Maya. Volcanism of large igneous provinces is the probable culprit for the second spike, the Cambrian Ordovician extinction. The rapid release of sulfur dioxide likely cooled the planet and increased the sulfur in the oceans. The resulting catastrophe is more well known, but ironically less deadly. Only around 25 to 30% of marine genera died during this later spike. The reason the later spike is more well known is because of what came after. By the end of the last Cambrian extinctions, there were higher levels of hydrogen sulfide in the oceans. On top of that, they were much cooler than they had been during the third biotic age. These changes drove the Great Ordovician biodiversification event. It saw the very potent net speciation of the phyla which had evolved out of the Cambrian explosion. It is worth noting that it was these same changes that punctuated the last Cambrian extinctions. This shows that major extinction events come about more so from the abruptness of a change, not the change itself. The Gobi abruptly ended around 445 million years ago due to what appears to have been a cold snap. Sea levels dropped by 75 to 100 meters, destroying many ecosystems in shallow waters. These events marked the start of the end Ordovician extinction. The cold snap made many niches untenable. Species of warm equatorial reefs were hit particularly hard, as they had to contend with cooler waters. In total, about 30% of marine genera died out. As devastating as it was, life was left standing at the conclusion of the end Ordovician extinction. Many species of fish, scorpions, trilobites, and cephalopods were among the noteworthy survivors. At the start of the fifth biotic age, the reefs that were decimated by the end Ordovician extinction recovered. Eventually, the marine life that made it through began to diversify rapidly. Around that time, the first jawed fishes evolved. One of their subgroups, the ray-finned fish, are thought to be the direct ancestors of modern bass, tuna, and salmon. The oceans, however, were not the site of the most dramatic changes. During the tail end of the fourth biotic age, stretches of low-growing vegetation clung to the coasts. Consequently, the continental interiors were left largely barren. All of that changed during the fifth biotic age. During the so-called Silurian-Devonian terrestrial revolution, life left the confines of water to colonize dry land. It did so through the successive spread of trophic levels inland, eventually culminating in full terrestrial energy pyramids. These developments were kicked off by the evolution of roots, broad leaves, seeds, and vascular tissue. Roots allowed plants to anchor themselves to the soil securely. Broad leaves increased the surface area to trap light for photosynthesis. Seeds protected plant embryos, whereas vascular tissue allowed for increased structural support and upward transport of nutrients. Lycopods were among the first vascular plants to evolve. They then rapidly diversified into the definitive life forms of the fifth biotic age. They made up most of the producers on land. In time, primary consumers like millipedes and flightless insects evolved to consume them. Primary consumers were eaten in turn by secondary consumers like spiders, scorpions, and centipedes. The ecosystems that formed were dominated by gigantic arthropods. Vertebrates were relative latecomers when it came to the colonization of land. They only began moving out of the water following the development of the first canopies. Lobe-finned fish evolved into the first amphibians. Tiktaalik was likely among the first to do so. It is notable for directly showing this transition from aquatic to terrestrial features. The Silurian-Devonian terrestrial revolution ended around 360 million years ago, well before the end of the fifth biotic age. The next 100 million years were characterized by slower net speciation. The effects of this later increase in diversity were a far cry from the colonization of virgin lands observed in the earlier 85 million years. Most noteworthy changes that occurred instead saw new species supplanting those that had become established during the terrestrial revolution. One such change seems to have caused another. It was the sharp increase of early conifers and cycads, which came at the expense of lycopods. The resulting decrease in oxygen caused the disappearance of the giant arthropods, which occupied most niches. Egg-laying vertebrates evolved in their place, and they quickly came to dominate the land. A similar process occurred with endoptery goats, insects undergoing four-step metamorphosis. They became more common as the biotic age progressed, largely supplanting other insect groups that were already established across many niches. The fifth biotic age lasted 185 million years, the longest of the 8 biotic ages. During those 185 million years, the biosphere experienced its most dramatic expansion. Life, having previously been confined to the oceans, ventured out into dry land, and set about rapidly colonizing it. For that reason, it can be thought of as double remarkable. It is only fitting then that the major extinction event that ended it all was equally remarkable. Around 260 million years ago, the biosphere was devastated by a cataclysmic event from the lithosphere. Increased volcanism injected large volumes of greenhouse gases into the atmosphere. The resulting high temperatures made many niches untenable. These events triggered the start of the last Permian extinctions. The last Permian extinctions consist of two major spikes in extinction intensity. The first was the Capetanian extinction event, which occurred about 260 million years ago. It killed off some 35% of marine genera. The second spike occurred around 250 million years ago. It is the deadlier, more well-known one. Called the Great Dying, it saw some 50% of marine genera go extinct. The last Permian extinctions are by far the deadliest of the 7 major extinction events. Taken as a whole, they are likely responsible for the extinction of around 95% of animal species. They thus mark the closest that multi-celled life has ever come to total extinction. The 5% of species that managed to survive include some fishes, marine reptiles, temnospondyls and therapsids. Following the last Permian extinctions, the world was left ripe for the taking by its few survivors. Life quickly recovered. The niches left vacant were mostly filled by reptiles. They quickly came to dominate the sea, air, and land. In the seas, the surviving marine reptiles evolved into ichthyosaurs and plesiosaurs. In the air above, pterosaurs evolved, becoming the first ever vertebrates to take flight. On the land below, a group of reptiles called archosaurs took advantage of the new open world. 3 advantages helped them rise to the top: relatively light skulls, teeth set in deep sockets, and a unidirectional respiratory system. Around 240 million years ago, the first dinosaurs or bird-line archosaurs appeared. They eventually diverged into theropods and sauropods. Though dinosaurs evolved during the 6th biotic age, they did not spend it as masters of the land. That title was reserved for early Pseudosuchians croc-line archosaurs. They came to occupy many niches, encompassing apex predators, piscivores, pursuit hunters, armored herbivores, and scavengers. It wouldn't be until after the end, Triassic mass extinction, that dinosaurs would come to rule the world. The 50 million years of net speciation ended around 200 million years ago. The cause was a cataclysmic event from the lithosphere. The rifting of North America from Pangaea caused a spike in volcanic activity. The resulting rise in greenhouse gas emissions kicked off the end Triassic mass extinction. The end Triassic mass extinction killed off some 30% of marine genera. On land, it most visibly manifested with the extinction of temnospondyls, and most of the large Pseudosuchians. The breakup of Pangaea and the formation of the Atlantic Ocean brought previously isolated communities together. The subsequent increase in competition led to the Mesozoic marine revolution. It was a period characterized by a rise in shell crushing and boring predation. The ocean saw a sharp increase in planktonic and in faunal lifestyles. The change was so far-reaching that they now characterize most modern marine life. The 7th biotic age saw life on land evolve in a similarly dramatic manner. The first flowering plants appeared and largely supplanted conifers and cycads. The disappearance of large Pseudosuchians had left many niches wide open for dinosaurs and pterosaurs. Dinosaurs rapidly diversified into those vacant niches, eventually becoming the definitive life forms of the 7th biotic age. Many new adaptations emerged from this diversification. One such adaptation was the development of expanded guts and large chisel teeth in Ornithischians. These traits quickly helped them become successful, and they eventually grew to encompass diverse forms like hadrosaurs, ceratopsians, pachycephalosaurs, and thiophorans. Sauropods saw a massive increase in size, eventually developing into forms like the Giraffatitan and Argentinosaurus. Carnivores like Utahraptor and Yatranus evolved to eat smaller herbivorous dinosaurs. Tyrannosaurs, on the other hand, fed on the larger Ornithischians. Another notable development was the increase in the size of pterosaurs, which culminated in the evolution of Ediacaran. The filling up of vacant niches led to a gradual decline in net speciation rate, especially towards the very end. In some groups of dinosaurs, the trend of growing diversity seems to have reversed altogether. This was the case in ceratopsians and hadrosaurs, which became less diverse from around 75 million years ago. It wouldn't be until the KPG extinction's onset that non-avian dinosaurs as a whole would experience a decline in their diversity. Net speciation abruptly ended around 65 million years ago. Excavations of the Deccan Traps in India show evidence of large-scale volcanism from around that time. While some explanations point to this volcanism as the main culprit, it likely had very negligible effects. The cataclysmic event that truly devastated the biosphere was the impact of a giant asteroid in the Yucatan Peninsula. Large volumes of ash filled the atmosphere, creating a long impact winter that starved plants and phytoplankton of light. With producers compromised, many niches on higher trophic levels became untenable. The resulting KPG extinction killed off some 30% of marine genera, including plesiosaurs. On land, ceratopsians and sauropods were among the first to go. In time, all non-avian dinosaurs fell victim to extinction. Like all major extinction events, the KPG extinction had its fair share of survivors. The most notable are birds, crocodilians, and true mammals. True mammals likely evolved at the very start of the 7th biotic age. For the remainder of its duration, they were confined to minor roles. Their opportunity to become major players would only present itself following the KPG extinction. At the start of the 8th biotic age, almost all of the world's large land vertebrates were gone. Many of the niches they once occupied were left open for exploitation by the creatures that had survived the KPG extinction. Their diversification into those vacant niches occurred quickly. Within 5 million years, birds were diversifying into forms like Waimanu and Psidiaceae. Trophic levels that had previously been decimated were gradually rebuilt. Ungulate mammals assumed the role of primary consumers in this new world. The role of secondary consumers came to be filled by creodonts, the descendants of surviving insectivores. They would later be supplanted by the felines and canines we are more familiar with today. The primate lineage appeared. It initially manifested as the primate-like Purgatorius, eventually developing true primates like Onomyids and simians. Ice sheets formed in Antarctica around 35 million years ago. This decline in the biosphere's size caused a corresponding decline in net speciation rate. This period of slower net speciation continues to this very day. A chart documenting the number of genera shows that there were 2,000 genera around 65 million years ago. That number had risen rapidly to about 4,000 around 35 million years ago and has continued to rise since, but much less drastically. It is not surprising then that after 35 million more years, it currently stands at just 5,000. Despite that though, two notable developments still occurred. Firstly, the drop in both temperature and humidity led to the first grasslands appearing. Compared to leaves, grass is more fibrous and harder to digest. By virtue of possessing a rumen, ruminants had an advantage in consuming it. They quickly capitalized on it, eventually becoming the main grass-eating ungulates. Secondly, the first apes appeared about 20 million years ago. They quickly diversified, growing to encompass both lesser apes and great apes. It was from this diversification that humans evolved and spread across the planet. They have made many technological advancements since, because of their ability to transmit knowledge across generations. Unfortunately, the creation of this unique legacy has negatively impacted biodiversity. At this moment, we can only hope that humanity finds a way to check these destructive effects. If not, they will very likely trigger an 8th major extinction event. The history of multi-celled life is one of successive, biotic ages being cut short by major extinction events. I believe I have adequately justified that position. After describing the underlying processes, I periodized the last 575 million years into 8 biotic ages, separated by 7 major extinction events. I then showed the processes I described earlier in action. I have looked at all 8 biotic ages, but I really want to focus on the 2 most recent. For that reason, I intend to make videos on the 7th and 8th biotic ages later this year. Until then, thank you for watching.